So for a lot of schools, right, they just teach hybridization as it is, right? That means it's like that because it's like that. I prefer to teach why it's like that before going to all the details, right? So now if you can recall from what you have learned in chemical bonding, right? In chemical bonding, we have learned about simple bonds being formed by overlaps. So for example, you have your P overlap sideways, right, to form a sigma bond, and you can also form sigma bond by SS overlap, right? So these might seem sufficient at that stage, but you realize that as we do more and more of chemistry, there are actually some problems, right? So for this part, I will assume that you already know these three. First is describe the relative energy levels of atomic orbitals. This is related to your atomic structures, right?
Yeah.
So this is the one, S, P, you know how to draw this. And sketch the respective atomic orbitals, S, P, and D. Wait, if you are taking this year, are you taking under new syllabus or old syllabus? Okay. Because for old syllabus, you're not required to draw the D.
Yeah, but I think I'm needing it.
Yeah. So describe a covalent bond as the sharing of electrons. This three you have to know. So hybridization is the mixing of atomic orbitals into new hybrid orbitals. So previously, like what I said, right? You already learned about orbital overlaps in chem bonding to form sigma and pi bonds. You learned that pi bonds are formed by pp overlap, right? In addition to the sigma bonds which I said just now. So why is hybridization necessary when this concept can basically explain the phenomena, right? We'll use some examples to see what goes wrong. So first thing we'll look at is CH4, right? So for CH4, if we were to draw the energy orbitals, this 2p, this 2s, we know that carbon has got 4 electrons, right? So its configuration is like this. So now we know that from chemical bonding, we learned that in order to form a bond, right? For example, an orbital need to have 1 electron, another orbital from another atom or whatever species have 1 electron, and then they overlap to form that bond. So in theory, this one should be able to form this compound CH2, since there's only 2 lone electrons, but we know CH2 doesn't exist. The most stable form is actually CH4. So what is actually happening? We can't use what we have learned in chemical bonding to explain this. So this is the first problem. We'll call it the number of bonds problem, because obviously you don't form that number of bonds, right? Okay, what's the next problem that you'll encounter? Let's say water, right? So for water, H2O, what is the electron configuration for oxygen?
Electron 1s to 2s to 2p 2p and the
Yeah.
oxygen 16.
Why do you have 2p? This is 1, right? This is 2, and you only stop at 2. You don't go to 3. Right? If you refer to the name card, you realize that I've already classified them under S block, P block, etc.
Oh, this is P block. Wait, below is 2, 6. We have 1 is 2p 2 1 is 2, 2 is 2, 2p 2.
What's the configuration of barium?
Oh wait. 2 is 2p4.
2p4, right? This is S1, S2, P1, 2, 3, 4, 5, 6, D 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, F1 until 14. Okay? So this is a P4. So it's in period 2, so it ends with a 2p and a 4. So 2p4 means there are how many electrons here? 4, right? 1, 2, 3, 4. So I hope you know how to draw, right? This is your Hund's rule. So this means that there isn't any number of bonds problem for water, since just nice I have 2H and have 2H. But remember that if I want to draw out the how the orbitals looks like in a 3-dimensional way, right? X, Y, Z. I know that this is my X, Y, and Z orbitals, and this is my 2s. So in theory, I will have one lone pair in the x, one in y, and one in z, and of course 2 in the s now, right? So in theory, hydrogen should come in from here to form a bond, and other hydrogen should come in from here to form the bond. So now, based on this model alone, what will be the bond angle? 90, correct? Based on this bond angle alone. But is the bond angle of water 90? It should be 105 degrees, correct? So now, although there's no number of bonds problem, but we see that the bond angle doesn't really relate well. So there must be another problem. We call this the bond angle problem. Okay. So then, before we talk about how we solve this problem, right? You can actually fill in the blanks, right? So the expected stable species for this will be CH2, right? That's the expected stable species. For water, it's just H2, since there's no number of bonds problem. And then the expected bond angle for H2, we say that is 90. I already proven to you. But what about CH4? What's the expected bond angle?
109.5.
You sure? That's not the expected.
That's the actual.
That's actual, right? So the expected, same thing. Remember just now that case, we have this scenario. So if we have like this, we are going to end up with 90 degrees as well, correct? You can see why, right? But we know that the actual is 109.5. For water, the actual is 105. So you can see that basically the valence bond theory fails completely from what we have predicted from the actual. So there must be some problem, right? So in order to be more familiarized with the problem, you might want to try example 2, right? To see what problems there are. So remember there are 2 problems, right? How did I prove just now to show that there's the number of bonds problem? I drew this, right, to show that, well, you know, the number of bonds for this is 2. So for boron, since it has got 3 electrons, right, 2s2 and 2p1, that means it must be like that. So obviously there's the number of bonds problem, because in theory it should only be able to form BH, but now it forms BH3. So now you have the number of bonds problem once again. And what about the bond angle problem? Basically for this you don't even have a bond angle, right? Since there's only 2, right? So obviously there's a bond angle problem, right? So next part. So therefore, in order to bypass the problems, the concept of hybridization was introduced. So hybridization is actually just based on its name, right? The mixing of orbitals to give a set of degenerate orbitals to describe the inadequacy of your valence bond theory. So that's why we need to learn the new principle called hybridization principle, right? The rules of hybridization. So we will learn about the how of hybridization before we come back to see how you will solve the problems, right? So before we go into detail, we will need to keep in mind 2 very, very basic rules. The first rule is that the number of electrons before and after you mix is the same. It's just like blending juice, right? You blend 100 gram of apple and 100 gram of pear, you get 200 gram of juice. You don't get 100. Same as this, right? Number of orbitals before you mix and after you mix is the same. In other words, the number of lines, right? Before you mix and after you mix is the same. So let's look at the sp3 hybridization first, right? So you just have to refer to this diagram. So beforehand, we have these orbitals for carbon. You can ignore 1s since it's in the inner shell, right? So the first step of hybridization will be to promote 1 electron from 2s to a 2p, right? So once this promotion, you're going to have this kind of scenario, followed by step 2. Step 2, what you do is you mix this orbital with these 3 orbitals together. So we are still obeying these 2 rules. Number of electrons before is 4, afterwards is also 4. Orbital is 4, afterwards is also 4. And take note of the relative energy levels. The final one is somewhere in between, because you mix them together, the energy is going to lie somewhere in between, of course. Okay. So whatever you never touch, it will remain there, right? Nothing else is affected. So after doing so, right, the 2s and 2p and the 3 2p orbitals are replaced by 4 sp3 orbitals, which arrange themselves in a tetrahedral kind of fashion in this way to minimize repulsion, which is your VSEPR theory. So originally you have these 4, after mixing they are gone completely, and you're gonna get 4 new degenerate orbitals.
But then how we know we like this one we have to memorize that we count a tetrahedron.
Remember, this is not memorized, this is about your VSEPR theory, right? Imagine I have an explosive object, right? Just nice it break into 2 pieces. Will the 2 pieces fly this way? Not like that. You most probably, do you take physics?
Yeah.
You take physics, so you know something called conservation of momentum, right?
Yeah.
This is actually part of your conservation of momentum. So if you have 2 pieces, you'll fly like that. If you have 3 pieces, of course you'll fly 120 degrees apart. Right? For this, you have 4. The only way to balance out everything is to fly in a tetrahedral way. And this is the way. This is the only way to minimize your repulsion, right? So it's the most favorable way, right? Atoms are also very, very smart. They want to be as stable as possible. So now, in ethane, each carbon is sp3 hybridized, and 3 of these sp3 orbitals overlap with the 1s, or the other one overlap with the other counterpart, right? So that's how you form your sigma bonds. Okay, So now, how does this solve your number of bonds problem? Is solved by here, right? Originally you can only form 2, but after hybridization you have 4, so each of these can form 4. So you solve the number of bonds problem. What about the bond angle problem? Is solved as well by minimizing repulsion, so everything is 109.5. So now everything solved, right? Using hybridization. And just take note, these few steps doesn't mean in reality it occurs this way. All of these occur simultaneously. I'm only writing as step 1 and step 2 to make it easier to understand, right? So other examples of sp3 hybridization are these 2. So now we know that this one resembles ammonia, right? So maybe you can use the same concept to deduce the hybridization state of this.
Wait, if you ask for hybridization state means what? Like sp3, sp2
Yeah.
or sp. sp3. It's sp3, right?
Yeah, prove to me using this. Why is it sp3? I know that it's quite simple, right? But what if I give you a more complicated example? Later on you will see, right? You won't be able to tell unless you use this method.
Nitrogen is good 5. So this one.
Which rule do you not obey? Remember, you always have to obey these 2 rules.
Same number of electrons.
Do you have the same number of electrons before and after you mix? See, you are already violating the first rule, right?
Yeah, one more missing.
So, although it's very simply, a lot of people just simply say, oh, it's sp3, but they don't know how to draw this, right? So how should you draw? Just pair them up, right? That's the only way, isn't it? Nobody say it cannot be paired up, right? So that's the problem. A lot of teachers just teach sp3, sp2, blah blah. So a lot of students will think, oh, sp3 can only be applied to carbon, or there's only sp to sp3 hybridization. There's nothing else. In fact, there are other hybridization states as well, like d2 sp3. Have you seen such before?
No.
No, right? Later on you'll see some prelim questions which actually ask this, right? You sure there's 2s? Remember, you're not obeying the second rule, right?
The number of means.
Before you have 1, 2, 3, 4. Afterwards you have 1, 2, 3, 4, 5.
Oh, that means no more.
Yes, remember? I said once you hybridize it, it's gone completely, right? So how you adopt this kind of shape as well, correct? So a lone pair will be in one of the orbitals, one electron, which will bind to hydrogen or whatever other species. So by VSEPR theory, lone pair bond pair repulsion is greater, so that's why its bond angle is 107. So it explains everything, right? You can go back and try for this. It's the same, right? I will not go through the second one. Okay. So next one is sp2 hybridization. So same thing, I will cut short, right? Since it's the same step. But for this case, first step, what you do is instead of after you promote the electron, instead of mixing everything, you are only mixing this with 2 of it, right? So after you mix this with 2 of it, what do you realize about the energy level? You'll go somewhere in between, correct? Did we touch this one?
No.
No, we didn't touch. So it remains where it is, right? So after hybridization, 1s and 2p orbitals are replaced by 3 sp2 orbitals, which arrange themselves in a trigonal planar geometry. Same thing, the aim is to minimize repulsion. Take note, originally you have 3 of the p and 1 of the s. Just now you mix everything together, so everything is gone. Now remember, you didn't mix this one, so you're only mixing these 3. In other words, the final resultant orbital diagram consisting of everything will look like that. Why does it look like that? Because this one in this axis, we never touch it, so it remains there. These 3, which we touch, is gone, so it's replaced by this. So most of the time, we are only focusing on the hybrid orbitals, these 3. So if you were to remove this one, you'll look like that from the top view.
So when you ask for hybrid, you just
yes,
without
just this.
the one.
Yes, this is to illustrate that this remains there.
Yeah, but why is it not possible for like this, like maybe 1, 2, 3, and this one to mix or
Also
like
can.
that?
Also can.
Oh, but you will get the same shape then.
You will get the same shape, right?
Okay.
Just like you mix apple with pear or mix pear with apple, the order doesn't really matter, right? You'll still get the same thing, right? So this is the shape you will get. So in ethene, each carbon is sp2 hybridized, right? And then 2 of these overlap with, basically you can just look at this, right? This diagram, this orbital is actually this one. That's why I drew this, right? So this is hybrid. This is non-hybridized, this is non-hybridized. So the hybrid orbitals will overlap with the s, the 1s of H and with each other to form the sigma bonds. While the p orbitals, they are parallel to each other, so they overlap sideways to form the pi bond, right? Take note, one pi bond got 2 electron regions, right? So same thing, you can have other atoms that exhibit sp2 hybridization. So same thing, I want you to use this method to deduce why they are sp2 hybridized.
This one is not included for hybridization, right? Then why we draw, we still need to like draw it.
What do you mean?
Cause just now say this is not hybridized, right?
Because
but we still leave it as
because if you don't draw this, then how are you going to illustrate the pi bond?
No, okay.
Right?
So now this.
Yes.
You want to draw this also, right?
Yeah, to deduce why this is sp2, the boron species. So as to solve this problem, right?
But now boron got 1p.
Remember, just now, what makes you mix these with 2? What makes you mix? There's a nitrogen. What makes you mix the S with 3 of the P? It's because you have to form 3 bond pair and 1 lone pair, correct? 1 lone pair requires how many electrons? 2 electrons. So 3 of the bond pairs require how many electrons? 3 lah. So 2 plus 3 give you 5. So you need 5 electrons, correct? So for this case, you need how many electrons? 3. So that means you have to mix these with each one. Definitely with this one, correct? But remember, if you mix these with these, you're going to have 3 electrons, yes. But do you have 3 orbitals? No, you only have 2. So you need another orbital to fully bind with the 3H. So you need another empty orbital, right? So you actually require these 3 or the other three, doesn't really matter. Remember, your relative energy levels are wrong, right? So after you mix them, the energy is gonna lie in between, right? Remember, in order to form 3 sigma bonds, right, you need 3 lone electrons in each orbital.
Yeah.
So you cannot have this, because this one would mean that you have a lone pair, isn't it?
Yeah. Oh, so I think it's draw 3 orbitals.
Yes.
Oh, yeah.
You sure? You're obeying these 2 rules once again?
No, okay. 3. Oh, there's still one more orbital.
Where's the orbital?
Just
You
remember.
sure it's there?
Oh, go up.
Remember which one do you hybridize, which one you didn't touch?
2s and 1.
So you hybridize
Yeah.
this and this, right? Do you touch this? No.
No.
So this is gonna remain where it is. These 2, after they hybridize, its energy level is gonna lie somewhere in between. So it should be lower than this.
One more above it.
Yeah, it shouldn't be below, right?
Yeah.
So how does it hybridize? I mean, how does it bind to hydrogen? One hydrogen bind here, another one will be here, another one will be here. So that's why it's sp2. Okay? So now, you realize that you learned the sp2 for using alkenes as examples, right? There's a pi bond. This one doesn't have pi bond. So doesn't mean that you know pi bond means sp3, right? I think some teachers teach it this way. They tell students, if it's sp3, that means it must be 4 sigma bond, 0 pi bond. If it's sp2, that means it will be 3 sigma bond, 1 pi bond. If it's sp, it will be 2 sigma bond, 2 pi bond. They teach this way, but then what about this?
This one is
Wrong what? Correct. So therefore, I don't teach this way, right? Because this one is a memorization way, this one is the understanding way. Okay, So next you try another one for this case.
This is double bond, right?
Yeah, it's double bond.
Nitrogen is 5. Like that. Wait, if it nitrogen or down?
Remember for this case, I demonstrate. So originally, your energy level is like that, correct? So now you then ask yourself, how many sigma bonds do I need? So for this case, I need 2 sigma bonds, right? So for every sigma bond, I'll need 1 of this. So since there are 2, that means I'll need 2 of these. So in total, I should have 2 of this. And on top of that, remember I have a lone pair. So for lone pair, I need to have another of this. So in total, I need to have 3 sets of hybridized these orbitals, right? In other words, right, all of these I must hybridize, right? So I only hybridize 3. So eventually, these 3 will become 3 hybrid orbitals. 1, 2, 3, 4. These are hybrid orbitals. I call it the sp2 orbitals. And the 2p, remember, I never touch, so it's going to remain where it is. So now, one hydrogen will bind to, or carbon, doesn't matter, right? Another one will bind to here, and then this one will be the lone pair. Pi bond is formed by the sideways overlap of this. So this is the diagram for the center one. Okay,
Yeah.
so you can try for this when you go back, right? It's the same. So lastly, SP hybridization, same thing, but for now you're only mixing 1 2s and 1 2p. Same thing though, those that never touch remain where they are, those that you touch will lie somewhere in between. So once again, if you have these 4 orbitals, you're only hybridizing these two, or these two, or these two, doesn't really matter, right? So for now, I'll just hybridize these two left untouched, so they will still remain where they are. And these two will hybridize to form a new set of hybrid orbitals. This one you have to know how to draw, right? So you add this to the unhybridized one, this is what you get, right? Which is exactly this. So in ethyne, this is the bonding picture in ethyne. You have sp hybrid orbitals. The sp hybrid orbitals will bind with H and the other one bind with each other. The unhybridized orbitals will overlap sideways, so you have 2 of them to form 4 electron regions consisting of 2 pi bonds. So this is how the bonding picture is like. Okay. So next you try this one. BH2C.
Like 1 2 sigma 1 don't play.
Where's your p orbital?
But I don't only have 4. Then it's empty.
Remember, you always hybridize valence orbitals. You don't hybridize one outer shell and one inner shell. Remember for this case, for this case, beryllium only have 2s electrons, right? So now once again you ask yourself the same question. How many sigma bonds there are? So there are 2 sigma bonds, right? So you're going to form 2 of these. Are there any lone pairs? No lone pairs. So it's going to be like that, right? So you need 2 of these hybridized. In other words, in order to form this, the only possibility is mix like that. Correct? So if you mix like that, you're going to have 2 orbitals, each with 1 electron. This is sp, and these 2, they are untouched. And this is how you get the sp to hybridization state. Okay,
Then the bottom one just leave it.
The bottom one.
The 1s.
The 1s. Remember, hybridization is about valence. In fact, for all of these examples, you realize that the 1s does nothing. Right? So in fact, we can just leave out 1s since it's useless. Right? Next, example 3. Why is it very difficult?
Because I'm not familiar, or because I haven't really revised on atomic structure, because it's very small.
Okay. Why not for this case I demonstrate the first one, right? And then you can do the second one. So now you have your SF6 and PCl5, right? I'll do SF6 first. So for SF6, same thing, write the configuration. So for sulfur, it is 3p4, right? So now we have 3s, 1, 2, 3, 3p, right? 1, 2, 3, 4. Okay? So now if I want to form SF6, there's definitely problems, right? Because based on this picture alone, I know that I can only form SF2. SF2, right? And of course, if there's a number of bonds problem, there will be a number of the bond angle problem. So how do I overcome this problem? Same thing. Remember, just now I say that I have to ask myself how many sigma bonds I have. I have 6 sigma bonds, so I'll need 6 of these. Do I have any lone pair for SF6? I don't, so I need 6. But how can I ever form 6 when I only have 4 orbitals in total?
You use the higher one.
Yes. Nobody say you can't, right? And you already learned that the elements here have low-lying vacant d orbitals. So that's where it comes into play, right? So since I need 6, 1, 2, 3, 4, I need 2 more. So these 2 come from here. In total, I have 6. How many electrons I have? 1, 2, 3, 4, 5, 6. Just nice, I can form 6 of this. So this is going to get mixed together. 3, 4, 5, 6. And form my 6 orbitals, right? This one is the new one. And how do I name it? Make a guess.
3D something.
You sure? Why is it called SP3?
3 because you mix S and 3P.
So for this, what will be the name?
This one is P, right? P. P6 something.
Why P6? Why is it called SP3? Because there are 3P is made of 3P and 1S. So for this,
make up P3 2D 1S.
so is what?
P3
P3 what?
D2
And then,
S1.
do I write 1?
No, just
I don't write 1.
S.
In fact, yeah, you are correct. This is the hybridization state. And then you will think, tested me. Right.
Yeah.
Then I would say knowledge is power, right? If you think it's not tested, then let me see. Nothing to say, right? You might want to try this 2009 question.
Oh,
So you won't say, oh, it's a new concept, blah blah blah. Yeah.
which form of orbital can form this one? Square period.
This is not Excel one. This is RJ 2009 prelim.
Yeah.
On one look, you know that there's something wrong, which, of course, right, something you have never learned before. I'm only giving you the example. You don't have to do it now. Right? Another one. The following table shows the 3 compounds and respective types of hybridization. This one, SP, SP2, SP3. From the data above, deduce the type of hybridization in PCl5. The answer is DSP3. Okay, 这个不是 joke. In fact, I started teaching this even before they gave the example, right? Because, well, this is understanding concept, but this is not syllabus, right? So in fact, this is D2SB3, which is what you called just now, or you call it SB3D2 also can, right? Doesn't matter. So if you do the same for PCl5, right, you're going to end up with VSP3. It's the same concept. Okay, so you can just write down the answer for now and go back to think about it. Anyway, you can just view the video again, right?
Sure.
So the previous part might look a bit difficult to you, but there are actually some simple ways to deduce what hybridization state they are, and here I have summarized it here, right? Beforehand, I must teach you the concept first, right? Before I tell you the summary. So as a shortcut to determining hybridization state of atoms without analyzing it in this kind of troublesome way, this is what you have to do, right? Just ask yourself how many sigma bonds there are. So for every sigma bond, you will need one hybridized d orbital. For every lone pair, you will need one hybridized d orbital. And for every pi bond, you will need one unhybridized d orbital. Afterwards, you just have to count the total number of hybridized orbitals used. In other words, if you have one of these, two of these, total is 3 lah. One of these, 4 of these is 5, right? So just based on this, you can deduce what's the hybridization state. For example, if I use PCl5, right? So first I'll draw the structure of PCl5. You should know, right? It's the star, this thing, correct? It's not star shape, it's a trigonal bipyramidal, right? So for every sigma bond, you need 1 hybridized. So in total, you need 5. There's no lone pair. So total number of hybridized orbital is 5. Refer to this table, DSP3. Very fast, right?
Yeah.
In fact, this is the fail-proof method, right? The above method applies to all atoms, right? For all atoms, you can use this. But of course, this is just derived from just now the method. This is I derived, this is not taken from some textbook, right? But if it's for carbon, nitrogen, or oxygen centers only, another method exists, but it's for carbon, nitrogen, oxygen centers only, okay? For this case, it doesn't work. For this case, it doesn't work because it's not these 3, right? The method is just this, which I told you just now. If there's 2 sigma bonds, 2 pi bonds, you'll be sp. 3 blah blah blah. Then you can read, right? Yeah. So it's either this or this. If you are hardworking, this one is sufficient.
I usually use this.
So that's why I say, try using this on this, you'll get it wrong, right? Because this one doesn't fit any. So that's why I don't teach this first. Okay? Yeah. This is the fail-proof method, right? You can go and stun your whatever lecturer friends. So next is about S character. S character is heavily related to hybridization, right? So hybridization is like blending of orbitals. So of course, different proportion of ingredients you get will give you different flavors. So if you were to compare all the orbitals from S, this is pure S, this is pure P, and this is SP, SP2, SP3. This is how the orbitals actually look like. You realize that as you go towards here, it gets more and more round. As it goes here, it looks more and more like P. This is just like your juice, right? You have 99% apple, 1% pear is going to taste like apple, right? So for SP, we can calculate the percentage of S character, which is 50%, 33, 25, and so on, right? So why is this useful? We know that orbitals with greater S character will have electrons closer to the nuclei. Why? Based on this diagram just now, right? We know that the nucleus lies in here. So S is closer to a nucleus than P, right? Yeah. So that's why it's closer. So hence there will be stronger attraction and stronger bonds. So if we look at the example here, right? All of these are single bonds. This, all are single bonds, but they are made up of different overlaps. So for example, this is made of sp3, sp overlap, this is sp3, sp, etc. So I already summarized here all the sp, don't know what overlaps and their relative bond length, right? So this actually tells you how strong the bond is. You realize that from this you can see that the sp-sp single bond is much stronger than your sp3-sp3 single bond, right? Why is it much stronger? Is because, remember, I already said that for your sp, right, these are your sp overlap, right? And your sp3, remember, is more elongated because it looks more like that. So this is sp-sp, this is sp3-sp3, right? We know that the nucleus is here, here, and here. So if let's say I have an electron here, it's going to experience greater attraction because it's closer, obviously. For this, there's weaker repulsion, weaker attraction, right? So it's going to be weaker. So that's why for this case, the bond length is longer than this case, right? Yeah. Illustrated by this.
So you must know roughly how it looks.
You don't have to know how it looks, right? This is just used to illustrate, right? In case you don't know how to explain, because by drawing out usually it's easier to explain, right? So for this you have to know how to calculate the S character, which one has higher, greater S character, etc. Right? So you can try examples 4 to 7. Basically it summarizes the whole section. Single bond. without the knowledge of these, you would think that all CC bonds are of the same length, right? Same strength, which is wrong. This is what?
This is this SP.
Mm-hmm.
This one is wait, your H also. It's all the SP.
So is which one?
Wait, this one is this one.
Yeah, it's that one, right?
Yeah.
So the next one.
Wait, what is wrong with this? Something wrong here.
So what's wrong?
How come half of the thing?
So what should the correct structure be?
All the way. Okay.
Does it look weird?
Yeah.
In fact,
Yeah,
as a trained chemist, whenever you look at this, whenever you see this kind of structure, you want to punch that person, right?
This one go like very awkwardly.
So how should you draw it? This is actually testing you on hybridization, right? Just now we say that the sp3 hybridized atoms are 109.5, correct?
Mm-hmm.
Followed by sp2, which is 120. 120, followed by sp, which is 180, right? So now we can deduce that this atom is sp hybridized. SP, right? This is SP, which means this one should be linear. This one should be linear,
Yeah.
correct? Which means it should be this shape, the terminal ones. And we know that this is sp2, this is sp2, so therefore it should be 120 degrees. So it can either be the cis or the trans, since that's not the main point for this question. Followed by the benzene ring. We know that for the benzene ring, it is planar. There's only one way to draw it. For the two hydrogen here, we know that this is sp2 hybridized sp2, so it should be 120 degrees, right? For this same thing, it should be 120 degrees, NH2, right? For this same thing, it should be 120 degrees, so it should be like that. So this is the better structure, right? So even now, some teachers commit the same crime by drawing such bonds like that, right?
Okay.
Because they are not trained as an organic chemist. I am. Next, what is the hybridization of each carbon atom and shape around each carbon atom in these molecules?
Nice. How are thinking part, right?
So what's the bond and go?
How are
You sure? You do this one first and then you tell me. Alright. So you already, this is sp2, right? Are you going to tell me it's 120?
No.
It's for obvious reasons, it's not 120, right?
Yeah.
So whatever that I've said just now, is it a hard rule or soft rule? It should be a soft rule, correct? So in fact, you're right. It's highly dependent on how strained the molecule is. Whatever that I've said Of course, it only applies if, let's say, it's unstrained. Same thing for this molecule, right? If, let's say, I have this molecule, you know that all of these are sp3 hybridized. Are you going to tell me the bond angle is 109.5? No, right? I believe you have learned in primary school these 4 angles 90 degrees, right? So obviously there's a soft rule. Of course, in chemistry there are a lot of soft and hard rules. This is just one of it. So in fact, these bond angles are 90, right? Common sense. What about these 3? 60. So if this is 60, then what is this bond angle? Should be able to calculate, right?
Yeah, just 360 minus this.
Yeah, correct.
Then 150, cause 2 sides.
Yeah, correct. So it's sp, 2 hybridized, but this bond angle is that one, right? The one you have calculated. What about this? A bit tricky, right? The center one. So for this carbon, remember, you can always use this rule. So for the central carbon, you have how many sigma bonds? 2 sigma and 2 pi, so it's sp. Or you can use this. You need 2 sigma bonds, correct? So 2 means sp. Either way works. This is again sp. What about nitrogen? Forget it, right? Forget it doesn't mean they won't ask, right? Because that one is quite easy. Right, next one. So you can just use this, right? You cannot use this, right? Obviously. Why you write 5? Remember, see the underline. About hybridized, right?
So it's just 4.
So it's just 4 because for pi bond it's not, right? So it's sp3. So now, why do I ask these questions if it's so easy, right? I don't ask easy questions.
Yeah.
So for this question, right, what I'm actually trying to let you think about is about the pi bond. How is the pi bond formed? Remember, in order to form pi bond, you need one unhybridized orbital. But once you have sp3, how can there be unhybridized orbitals left? Since you already used all the p. Correct, right? So for this case, why do you think so?
Wait, can we expand on that, right?
Why not? Remember, that's p, correct?
Yeah.
P can have low-lying vacant d orbitals, so it's actually these d orbitals that is responsible for the pi bond, right? But anyways, you'll still get the same answer, right? sp3. Okay, so this is all for this section, right? So now you can practice some. This one. I'm not restricting to carbon, right?
Yeah.
Carbon is too easy, I don't ask carbon. See if you can do this question without referring to a table, right?
Oh my god.
Because in exam you don't have a table to refer to.
Yeah, I'm not sure.
You can learn to construct a table, right? It's actually very easy. Remember, you have your SP, start with SP, SP2, SP3. After all your S and P is used up, you just go DSP3, D2, SP3, and so on, right? So for SP, you will need a total of 2 hybridized orbitals. This is 3, 4, 5, 6. And you have the table.
DS.
So once you have reached a limit for S and P, then you go to D, right? So what's the hybridization state of this phosphorus?
sp3. It's sp3.
Correct. Wait. You sure it's sp3? 1 sigma bond, 2 sigma bond, 1 lone pair, right? So total you have 3 hybridized orbitals. So it should be?
sp2. I think it's D, right?
Why is it D? Which one? This is phosphorus, right?
Yeah.
For oxygen?
2, 1, 2, 3, 4. So it's
sp3, right? Is it sulfur?
6 sigma 1.
So it's
1. What is this?
D2 sp3, right?
Oh, yeah. You know what is this? Minus means
So what is this? Minus charge.
1, 2, 3.
What is minus charge? Minus charge is also a lone pair, isn't it?
Oh, it is.
Why not? Minus charge is a lone pair, it's the same thing, isn't it? It's the same, right? So it's also sp3.
Yeah.
So which one is missing?
sp2. Wait, sp2 is sp.
Where is sp2 then?
Wait, isn't this
sp2, right? sp3 you already have. Correct? This is sp3.
Yeah.
This is D2 sp3. You already have. The only thing that's missing is D sp3. Okay,
Oh, okay. Oh, not
right?
quite difficult. And then, wait, do you know all this stuff in A levels already? Or you only like after you went? So A levels you already knew all this?
Yeah.
Cause usually schools they don't teach us.
Usually, then how they test? They tell me. They don't teach us things, right? Because it's concept, right? You know, in schools they tend to teach examples, so a lot of students will think that that example is actually the concept, but the example is purely just an example, right? It's not possible for them to teach all of this, otherwise A level is going to take 4 years, right?
Yeah.
So therefore a lot of this you have to really do yourself, right? In fact, for the rest you can go and attempt yourself, right? So this is more or less done.
Okay.
You can try this first, right? So we have about slightly more than an hour.
What is this for?
The
Just
true,
like true false?
yeah. Just write TF. If you don't know, don't guess.
After.
Yeah, before.
Oh, before.
Right. So you just write T or F. If you don't know, just put dash. Right. Don't guess. Don't spend more than 10 seconds on one. Right. Are you guessing?
No, I mean this one only one cyclic ring, right? Yeah, I didn't want to change.
Be careful of the phrasing. I tend to play around with the phrasing also.
Yes.
That's a common mistake a lot of students. Never mind.
Oh, okay.
You look at isomerism differently, right? Once I've taught you everything. Am I very evil? Purposely rotate the molecule, right? Yeah, this is to not to make your life difficult. It's to ensure that you know how to, rotate molecules. Okay, let's go through. Go through this, right? After you go through this, I think more or less you'll know the answers anyways. So the first thing that I would like to go through is, since we are talking about isomerism, right, there can be a lot of different structures for the same molecular formula. So first I'll talk about the degree of unsaturation, or what some people call it the double bond equivalence, DBE, right? So imagine you are given a molecular formula of C7H10, right? How are you going to work out the exact structure? You could do trial and error, but you'll take a lot of time, right? So the degree of unsaturation, aka the double bond equivalent, is useful, and you just have to use a simple formula to deduce the number of double bonds or number of rings. I don't know whether you know this or not, right? Do you know this already?
No.
You know, right? Now this kind of this concept is actually very, very useful for structural elucidation kind of questions. You have done those questions before? Yeah. So the degree of unsaturation can help to determine the total number of multiple bonds and ring structures within the molecule. Right? It cannot determine the exact number, but it can determine the total number, but it's also very, very useful. So here's the origin of the formula, right? Fully saturated molecules contain the maximum number of hydrogens possible, right? They cannot be more saturated already. So for example, a fully saturated molecule containing 6 carbon atoms would have 14 hydrogens at most, right? They cannot have more. So if there's another 6 carbon molecule with only 12 hydrogens, it would mean that there could either be a double bond or a cyclic structure, right? So you can actually just refer to this. So if you compare these two, the formula, right, the number of hydrogen decreased by 2, right? If you compare these two formula, same thing, if it's cyclic, the number of hydrogen decreased by 2, although the total number of carbon is the same, right? So if I have 2 double bonds, it will decrease by 4. If I have 1 triple bond, it will decrease by 4 as well. So if I have 3 double bonds, it will decrease by 6. If I have this, I will decrease by, you can count 1, 2, 3, 4, right? So in total there are 4. So in fact, based on this, I can calculate what's the number of double bonds there, right? So for most of the time, elements other than hydrogens are present, and yeah, you can see how it affects the number of hydrogens. So for example, for all of these, these have the same number of carbon, right? They all contain 6 carbon. So for this case, I add 1 nitrogen, and I see that whenever I add nitrogen, this nitrogen brings an minus away 1 H. So its formula becomes this, no matter where the nitrogen is. It can be a primary nitrogen, primary amine, secondary, tertiary, doesn't matter. Right? The formula will still be the same. And the presence of any number of oxygen will not result in a change in the number of hydrogens, because basically we are just inserting 1 O between C and H. The number of H remains the same, no matter whether it's an alcohol, an ether, or whatever species, right? And the number of the presence of halogen will result in a decrease in 1 hydrogen, because chlorine exactly replaces 1 hydrogen, right? So if you do the mathematical deduction, which you can do so, right, you obtain this formula, right, which is already summarized here. So the degree of should be degree of unsaturation, right? It's just the number of carbon plus 2 minus number of hydrogen minus X, which is the number of halogens plus nitrogen, divided by 2. That will give you the double bond.
2 times the number of carbon?
2 times carbon, because in order to calculate this, you have to times the 2, right? So this one can be derived from whatever is here, but that's not the main point for this part, right? So the main point is just this equation. You can use this to deduce what is the structure, how many double bonds and how many rings there are, right? So by using this formula, you can try this example. another C there.
Only C, not CL.
Oh yeah, sorry, CL, right?
Yeah.
I thought I typo. This one mental calculation.
12 minus 2. 10, 5.
Yeah, it's just 5, right? So, how do you draw? Can you just draw one structure? 4 isomers. 4 structures which fits this description. There's definitely more than 4, right?
Is this a ring or
You can draw any 4, right? Be creative. If I tell you to draw a cat, you don't draw just a black cat, right? It can be orange cat, a cat with no hand, a cat with no tail. Remember, you must satisfy these 5. So there must be 5 double bonds or 4 double bonds plus 1 ring. I already drawn 1 for you, right? Which is here. You can take a look. 1, 2, 3, 4, 5. So I satisfy the 5.
Wait, this one, this one is degree means must be double bond or what again?
Double bond or ring.
Ring.
Right? Is the
Oh, ring is
illustrator here.
considered as 1.
Yeah, there.
Oh.
Because once you form the ring, you decrease the number of hydrogen by 2.
Ring is 1.
So this is number of multiple bonds plus a ring, right? So if your answer is 2, right, it can mean 1 double bond, okay, or 1 ring, or sorry, if the degree of saturation is 2, it can be 1 double bond plus 1 ring, or 2 double bond, or 2 rings, or 1 triple bond, right? So all of these possibilities. So for this case, you really can mix and match. There are really endless possibilities, right? I already have the second answer, right?
Wait, but then how, if you say 5 means can have 4 double bond or 1 ring or 3
Yeah,
double
can
bond, 2 rings, right?
Can.
But then wouldn't that exceed?
I only asked you to draw 4. What do you mean exceed?
I mean, I wouldn't exceed the number of carbon chain. I mean carbon.
No, you can form cyclic structures. I already drawn 2, right? See, it doesn't exceed anything. So 1, 2, 3, 4, 5, 6 carbon. 1, 2, 3 double bond plus a ring, 4th one plus another one here 5. Right? It need not be a benzene ring, what? You can draw a 4-member ring, up to you, right? 4-member ring, then maybe it's connected to another, I don't know, 3-membered something, right? Really, there are endless ways, right? So now, there, I can have structures like this as well, there. 1, 2, 3, 4. Okay, sorry, one carbon missing. I just replace it with carbon. 1, 2, 3, 4, 5, 6. Right. Number double bond equivalents 1, 2, 3, 4, 1 ring, 5, 2 rings. Right. Of course, there are other mix and match possibilities. In fact, for this alone, you realize that I can put the OH here, I can put a CL here, I can put the OH here, I can put the OH somewhere else. Right. So for this, I think you will go back and practice.
No, you're so very fast.
Huh?
Very fast. Oh my god.
No, it's really, there's nothing. It's just like I give you different color beads.
Oh,
What necklace can you form, right? So go back and try.
Yeah.
Next, structural isomers, right? This part is the easier part of this topic. So isomers are broken into two kinds, structural isomers and stereoisomers. Now I only talk about structural isomers, right? So there are three kinds, which is your chain isomers, position isomers, and functional group isomers. I already illustrated here, summarized here, right? So all isomers have the same molecular formula but different arrangement of atoms. You should have already learned that functional groups affect the reactivity. So if you change the functional group, means physical properties will change, right? So chain isomers, they are isomers that differ only in structure of their carbon skeleton. Functional groups unchanged, same chemical but different physical properties, right? So for example, this one, can you just draw a chain isomer for me? Yes, okay, this is just one of the many chain isomers. Next one, position isomers. Isomers with functional groups located at different positions, and they have same chemical but different physical properties. For this case, you must have the same carbon backbone, right? So can you draw another position isomer? Yes, okay. Last one is functional group isomers. Based on its name, you know that there must be a different functional group, right? So can you draw another one? Sure, the number of carbons is correct. You sure? Every time you draw the structure like that, a kitten dies. Remember what I said just now for last topic? For this case, you shouldn't draw it like that, right? It should be like that, correct?
Yeah.
The bond angle. So although cannot penalize you, it's just for aesthetics purposes. Yeah, can. Okay. So now there's another example here, you can try it. Last one. So it cannot be an amine, correct?
Yeah.
And the thing for amine is you cannot put it in between, right? It's still an amine.
Yeah.
So how? Well, try this, right? Is this still an amine? This is actually not known as an amine already, right? This is known as an imine,
Oh yeah.
right? So you can in fact do this. How many carbon? 1, 2, 3, 4, 1, 2, 3, 4, yeah. Just like that. It's a different functional group, right? This is just for info, the naming. So next, we'll talk about stereoisomerism. This is usually the more difficult part, so therefore I brought my models, right? So they have the same molecular formula and structural formula, but different spatial arrangement of groups. They are further classified under two types, geometric and optical isomers. So we'll talk about geometric first, which is the cis-trans. Geometric isomers have the similar chemical properties but different physical properties, right? But as you learn higher level chemistry, if you 想不开, right, you know that they have different chemical properties as well, right? So it's actually a soft rule, not really a hard rule. Next, boiling point. Cis alkanes has a non-zero net dipole moment because for obvious reasons they are this shape, right? So if let's say there's an electronegative group here, right, there will be a net dipole moment pointing upwards compared to trans whereby they cancel out, right?
Yeah.
So for boiling points, we are comparing dipole moments, net dipole moment. So that's why C has a higher dipole moment and hence a higher boiling point. For melting point wise, right, we no longer consider dipole moment because now we have to consider how effectively they pack. So here I've already illustrated these two. A lot of students tend to tell me, right,
Better packing.
yeah, this one better packing. They say that, hey, this one look like bowl. It's like I can just stack it like a bowl. But in fact, they are wrong because there are things here, right, which prevents you from stacking, just like this case. There's no way you can stack it compared to this. So you can see that this one can stack very, very nicely compared to this. So in a limited volume, right, this, you can pack more of this than this, right? This means that your trans alkene can pack better, means that it has a higher melting point, right? So in fact, your schools teach cis and trans in terms of alkenes, but don't teach them in terms of alkenes. So please unlearn whatever they have learned, right? So just imagine you have never learned cis trans before, right? So for cis trans to occur, two conditions must be met. First is restricted rotation, either by the presence of a double bond or a ring structure, right? I never talk about alkenes, just take note. Another condition is two different groups on each of the two adjacent atoms with restricted rotation, right? So these are the only two criteria. Nothing to do with alkenes, nothing to do with carbon. So now if the two bulky groups are on the same side, it's called cis. If they are on the opposite side, it's called trans, or sometimes we call it Z or E, right? But for H2, cis and trans is sufficient. So next is the CIP rule, just FYI, right? What the CIP rule says is that if let's say you have groups as such, it's very, very easy to tell this is trans, this is cis. But what if I have like X, Y, Z, W? How do you determine whether this is cis or trans? You have to use what we call the CIP rule. What the CIP rule says is actually, do you know IU pack? Heard of it before, right? This is the authority to name all the, give all the funny names to all the molecules and set all these rules. So what they say is they actually develop a systematic way to determine whether it's cis or trans. If not, some people call this cis and some people call it trans. It will be quite messy. So basically what it says is that first, look at the atom directly attached to the stereocenters. The ones with highest priority is the one with the highest atomic number and so on, right? So if let's say this is fluorine, chlorine, bromine, iodine, right? We will compare these two and find the one with highest molar atomic number, which is bromine. For this side, it will be iodine. So this will be a cis. Okay, this is the first rule. Second rule, if the two atoms are identical, then look at the atoms directly attached to them, right? In other words, if let's say all of these are carbon, it's like that, right? Carbon, 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 carbon. We cannot use the first rule. We look at the second rule. The second rule will be the next one that's highest. For these two, there's nothing. For this one, is carbon, carbon. So now it's trans. Very simple. Next. Yeah, this is how you compare cis and trans. So next, multiple bonds are considered as an equivalent number of single bonded atoms. What this means is that if let's say the thing bonded to it is this thing, right, you can expand it into this. Basically what it does is that C is connected to O 2 times and H 1 times. So you expand it, become O 2 times and H 1 time, and so on. Usually,
the C came from? Oh, just CO2.
no, this O is bonded to C 2 times, right? 1, 2. So this O is bonded to C 2 times 1, 2. Okay, so this is just for your info in case you're confused with cis or trans, right? So for now, you can try this example on your CIP rules, right? Yes, it's D. Very easy, right? Yeah. You sure it's CNH? Remember how you draw CNH? How you draw CNH? Wait, did I put a typo here? Is there a typo? CN. I think there's a typo, right? It should be C. It should be CHNH. Sorry.
Oh,
Right.
CHNH.
Yeah, it should be a CHNH, right? Which is this structure, right?
Oh.
So if you compare this with CN, CN will have a higher priority.
Oh.
Because for this case, you can expand it to CNNN. For this case, you can only expand it to CNNH. So NNN is greater than NNH, right? And the last one. Yeah, because it's larger, right? Very simple. Now, simple part finish. We are going to do the more difficult part, right? So here I'm going to just give you the generic examples. These are examples, these are not. Yeah, okay. So the first type whereby you can observe cis-trans isomerism is your alkenes, right? This is the example all schools give. So here you have the trans, you can draw the cis here, right? So of course, apart from CC double bonds, remember you just have to satisfy the two criteria. One is restricted rotation. So this one you can have restricted rotation and you have two different groups attached to it. This one you can also have cis-trans. Where's the other group? The other group is actually the lone pair. There's no H. Remember there's a lone pair. A lone pair can also act as a group, right? So in fact the lone pair is the lowest priority group because it's basically the lightest, right? So can you draw the Cs as well? Yes, right, you can have cis. Same thing if you have a E-min, like this case, you can also have cis-trans. So maybe you draw the trans, the cis. So we see that it need not apply to alkene, right? Of course, N, that's why I say generic examples, because N can be replaced by anything, phosphorus, arsenic, everything, right? As long as it's like that, you can have cis-trans. This is the first scenario. The second case is for your cyclic compounds. For your cyclic compounds, okay, for your trans, I already drawn for you the 1,2-dichloro butacyclo, 1,2-dichlorocyclobutane, right? So can you draw the Cs for me?
This one is the point out.
Remember, this is your trans. This is your trans, right? You will see from the top. Right, you see from the top, this is coming towards you, this is going in from you. Right, this is the Cis. Why is it called Cis? Because if you look at it like that. Why is it called trans? Because if you look at it like that, it's.
So just need to fit it without only. If I just draw something now.
So how do you draw the Cis?
Something here.
You sure? These two are stereoisomers. Remember stereoisomers? What's the definition of stereoisomers? They have the same what? Same molecular formula, same structure, just different spatial arrangements. If you draw it here, it's no longer same structure. Right? They will be called positional isomers.
We just change this.
Yes, correct. So this is the cis isomer, right? Whereby two of them are pointing in the same direction. This is the trans, right? And this satisfies the criteria, right? Remember the criteria is there must be restricted rotation, right? Do you think you can rotate this? You can't, right? It's locked within the ring. So this satisfies the second one and this one, right? Two different groups, yes. So you can exhibit cis and trans. There's no way you can twist it, right? Unlike this case, if I say it's just this case, then you can turn it, right? So for this case, you don't really have cis or trans.
So I think this one is point out, right? The black one is out.
Point out. Okay.
Yeah.
So now, just in case you don't know, can you draw the mirror image of the trans isomer somewhere?
Image
of the trans isomer. Yeah, correct. So these two are mirror images, correct? So now are these two the same?
same means what?
Are they identical? Of course.
Yeah,
Right?
yeah.
You sure they are identical?
I mean, you can
You
rotate.
build this. I built this for you. The first one. I built it for you. Do you agree it's like that? This one.
Yeah.
Like that. The second one I built it for you. It's like that, right?
Yeah.
Yeah. Okay. You tell me whether they are the same or not. Compare them.
Cannot.
Are they the same?
No.
They are not the same, correct? What does this example tell you? These two are what? These two are enantiomers, right? They are not the same. In other words, they are non-superimposable mirror images of each other. AKA, it is chiral. Correct? Okay? So although it looks the same, don't think that, oh, one in, one out must be the same. No, you always have to build these two models. See, they are mirror images, correct? But there's no way you make it the same. Okay?
Yeah.
So I hope you can learn from this example. Next, you draw this. Wait, don't fill in this box first. Just draw the trans first. Remember, trans you have to draw the dash and the wedge. So you draw it already, What do you realize about this trans? If you draw its mirror image, do you think it's the same? Its mirror image is also trans, correct?
Yeah.
I already given you the mirror image, these two. Are these two the same? They are once again not the same, correct? In other words, you can have two transforms. So the other transform will be CL pointing out, VR pointing in, right? Wait, by the way, do I have to tell you that the mirror image of this is exactly the same as this?
Same? Why? Not just...
The mirror image is the same as this.
It's not, isn't it like this?
Yeah, it's identical to this one.
This is...
See, if I have a cis, do I have to build the other one?
No.
The other one is like that, you just turn around, it's the same, correct? So I don't have to explicitly say, right?
Yeah.
This one is just, you have to imagine. So what about the cis form? Are these two the same? See, I have this, correct? The other one, I swap these two. Are these two the same? They're not the same, correct? So once again, you have this problem, right? In other words, this is chiral, this is chiral, this is chiral. Okay?
Yeah.
So remember, you have learned that formula 2 to the power of n to calculate the number of stereoisomers. Can you apply it for this case? And say that, oh, I have two chiral centers here and here, so 2 to the power of 2 is 4. Is it true? This is wrong one. This, and one of these, so in total you only have 3. You don't have 4.
So the formula cannot be...
Again, that formula is another soft rule, it's not a hard rule, right? But for this case, it applies. In total, you have 1, 2, 3, 4, right? 2 to the power of 2 is 4. Later on, I'll teach you an even better formula, right? So that's why you must unlearn all your stuff. Next one, alicyclic double bonds. You might have learned double bonds in a ring system cannot exhibit cis trans. It can only be cis, correct? But this is once again only partially true, right? So for example, you have cyclohexene. Can you draw the trans? Do you think you can draw the trans or not? Cyclohexene. Cannot, right? Cannot, right? So that's why there's only cis, there's no trans. That's a trap, right? But what if I make the ring bigger? Just fill in the trans first, the cis one first.
How do I draw this one?
Cyclohexene.
Yeah.
How do you draw? It's just a hexagon, isn't it? It's cis,
Just normal.
right? 2 on the same side. Where's your double one? It's hexene, not hexene.
Okay.
So next, let's talk about cycloheptene, right? For this cycloheptene, you realize that, hey, I can actually draw the transform. Why is that so? Now I have a cyclooctene, 8-member ring, right? But the concept is the same. So now can you tell me, is this a cis or trans?
Cis.
This is a cis, because obviously both lie on the same side. Can I make it a trans? Yes, why not? I just point this here. This is a trans, correct? So I can in fact allow it to exist in this form. Can you see that this somehow resembles this?
Yeah.
Why I can do this for cyclooctene? Because the ring is large enough, right? In fact, this is the answer basically, right? You can have cis trans for this, right? So you can draw the cis here yourself. This is cycloheptene, right? 1, 2.
7 is it?
It should be octene, right? That's 8. I won't give 7. 7 is too hard to draw. Right? So you just draw the pakwa there. Right? Like that, the pakwa. Right, with a double bond. And one more thing, what do you realize about this? It actually has another mirror image, which is different from this.
Different.
Yes, you can try to imagine, right? I cannot build another model because I don't have enough cover, right? In fact, this, right, this is one way. Another way is the other way, but you cannot do it using like that. You have to plug this out, put it here, and the other one plug it out, put it here. Then you can have the other isomer, right, which is like that, the other way around. And these two are mirror images of each other, right? So again, this is just for interest, right?
Wait, so this one is have or don't have? Have, but it's different.
What do you mean? These two are enantiomers, correct? In other words, this is chiral. Remember, I want you to unlearn your chirality, unlearn whatsoever. So now, assume that you don't know what is chiral or not, right? So later on, I'm going to teach you about chirality. Okay, So next, apart from all of these, you can also have square planar or octahedral structure of complexes. You have learned transition elements, right? Have you learned stereoisomers for complexes?
But I think they usually they never say the mechanism behind all of it. They just draw one example and show you.
So that's why, right?
Yeah.
So in fact, you can also have cis trans for complexes. For example, you have this XeF2Cl2. You can also have trans or cis, right? We know that Xe, that species, right, FFCl, right, adopts a square planar kind of structure. So the 2F can either be on the same side, which we call it cis, or they are on the opposite side, which we call trans. So you can fill in the blanks here. Of course, I go through a lot for transition elements as well, isomerism, right? And for next one, SF4Cl2, right? It is a octahedral complex, so the 2Cl, I won't draw that ever, the 2Cl can either be on the opposite sides or on the same side, ClCl, right? So this is known as, again, the trans, this is known as cis, right? By the way, here and here is the same as here and here, here and here, here and here, here and here, right? I hope you can see it.
This one is the one is transition metal one.
Yeah, transition metal. So now we have seen some of the generic examples, right? So that actually expands your understanding of cis trans, not limited to alkenes only. In fact, you see that I don't really place that much emphasis on alkenes, right? It's just here. I place more emphasis on the varieties, right? Next, optical isomers, right? So same thing, unlearn all your optical isomers, right? You're going to relearn. Optical isomers are mirror images of each other and have the same chemical and physical properties but different biological properties. Do you take bio?
No.
No, right? So for example, these two drugs, right? And you know, in your proteins, right, they are active sites.
Yeah.
So your drug will bind to those active sites. That's how it's active. So you have one isomer and its mirror image. We can see that for this isomer, all the specific interactions are well interacted, right? But for this case, you're actually swapping the OH and the H position to get the other isomer. We can see that the OH doesn't bind to this active site. And that's why this is less effective, because if it doesn't bind to your active site strongly, it can just get displaced very easily. So it's not very effective compared to this case, right? So in order to draw the mirror image, one very simple way, if it's like that, I'll ask you to draw the mirror image. You have to flip the, you just have to invert all the stereocenters. So if this is wedge, you go dash, this is dash, go wedge. If both are wedge, you just change both to dash. It's always like that. Right, so you don't have to think so much when you draw. The two mirror images are also known as enantiomers. The two enantiomers have optical activities as each can rotate plane polarized light in equal amount but in opposite directions, right? So if a 50-50 ratio of the two enantiomers are mixed, a race-mixed mixture is formed and there is no optical activity, right? So biological systems usually generate or use only one enantiomer, while synthesized chemicals are often race mixed, right? That's why these kind of natural products are very, very valuable, because they have high biological activities, right? So here is just for your info formula to calculate the specific rotation, how much you rotate, and you can just read it yourself. So that's just FYI, right? I aim to finish at least here, because the rest is just FYI, right? So although closely related, there's a difference between chiral molecule and chiral center. So first part of this will be dedicated to what is the difference between these two, right? So first, a chiral molecule. If a molecule is chiral, then it will have a non-superimposable mirror image, implying that it is optically active and that it rotates plane polarized light. Okay, usually, only the chirality of small molecules is significant to talk about, because most big molecules are chiral anyways. Because for most big molecules, there's a lot of chiral centers, right? But only for small molecules, you might only have, one chiral center or two chiral centers that will determine whether it's chiral or not. So if the question is asking for the chirality of the molecule, then two conditions must be met, right? First one is there must not be a plane of symmetry within the molecule. Secondly, there must not be a center of inversion within the molecule, although this is quite uncommon, right? As long as you break any of the rules, right, even if the molecule contains chiral centers, it will definitely be achiral, right? Because its mirror image will definitely be superimposable. Okay, so as we do some practice, you'll see why. So can you tackle the easier one first? Right? Why is it not chiral?
There's no form.
You must use these conditions to explain.
Wait, what is center of inversion first?
What is center of inversion, right? Very simple. I'm just gonna use this. Right? I won't plug in all the hydrogen. So if let's say I have this molecule, right? Okay, for this molecule there's a center of inversion. In other words, there's a center of symmetry. Why do I mean by that? Because at the center, this exactly reflects here, this exactly reflects here, and the hydrogens exactly reflect. This is what I call the center of inversion. Okay, what do I mean by the mirror plane?
This one I know.
This one you know, right?
Just I know.
Okay, and
This one got no plane of symmetry.
you sure?
What is looking up? This one.
In order for it to be chiral, two conditions must be met, right? In other words, as long as there is a plane of symmetry, it's not chiral.
But this one has no plane of symmetry.
You sure? There is a plane of symmetry, what? The left and right must be the same, right? So is there a plane of symmetry?
Oh.
For this, you have to be creative, right? You have to think of the possible cases. Right? So for example, this case, I already constructed it for you, right? C double bond O, Cl, this is a 3 hydrogen. Is there a plane of symmetry?
Oh, like here.
Yeah, there's a plane of symmetry, what?
Oh my god, must look like white.
Of course, what? Right?
Oh my god.
Remember, stereochemistry is about 3D. Stereo means 3D, right?
Okay, look here.
Take note, take note. See like that. It might not look symmetrized, but take note, this bond can rotate, right? So there's a plane of symmetry, right? If there's a plane of symmetry, that means this is not chiral.
Yeah.
Okay,
Okay, this one has symmetry.
Why?
Your left facing. So this one don't have. This one also got symmetry.
This is a what symmetry? It's a plane, right? You can just write below plane or something.
This one also symmetry.
So this is what? Plane, right? And then?
This one no. Wait, not this one no, this one.
So this is chiral, right?
Yeah.
So just circle it. Is this chiral?
Yeah. No, this is not. This
Why?
is symmetry.
Why? You sure?
Here, same.
This is bond to where? This is bond to where?
Double bond. Oh wait, this one is the two is different, is it? Because this one got
You see,
three double.
no, this is bond to where? These two are the same one, right? This is bonded to the position here. This is bonded to a position here. So this group and this group are different one,
Yeah.
isn't it?
Yeah.
So if different, that means this carbon should be bonded to 4 different groups, right? So it must be chiral.
This one should be chiral.
You sure? This is actually not chiral, right? I purposely said this question because you have to know how to see it. So you have to draw it out. This looks like that, HOOC, correct? For this side, do you realize it's another COH?
Oh wait. Oh, this
Right?
one.
So is this chiral?
Yeah.
It's not chiral, what?
Anyway,
There's a mirror plane which cuts like that, isn't it? Left and right is the same. So this is not chiral.
Oh yeah, wait. Oh yeah.
This will teach you a lesson on...
Oh yeah. So which one? This one. This chiral.
You sure it's chiral?
Oh yeah, you see this one can rotate, right?
Is this chiral?
No, it's not.
Think carefully, right?
No, this one is plane of symmetry. So you say this thing, say she can.
So is this chiral or achiral?
Achiral.
Achiral, you sure?
Yes.
Think about it again. Of the shape, right? You can rotate around which bond? Which bond you cannot rotate?
You can.
Can you rotate the pi bond? You can't, right?
Oh wait, yeah. Oh wait.
So it's chiral, huh?
Yeah, it's chiral.
To convince you. Convince you, this is the model that I've built, right? Is there a plane of symmetry? You don't cut here, right? Left and right is not the same, right? Do you cut like that? Left and right, are they the same? No. So this is chiral, right?
No, this one chiral.
This one, you sure?
No, at point far will cause the thing to be different.
If let's say I were to draw it out, right? It's very He's pointing down. Do you realize that there's a center of inversion here? What did I say about center of inversion just now? Is as long as there's a center of inversion is a chiral, right?
Yeah.
So for this case, if this is a center, the one pointing up after you reflect will point top. This one, of course, is a reflection. This is a reflection. So there is a center of inversion, right? How about this?
There's symmetry.
Symmetry, right? Again, you're falling into a trap, right? I love making traps like this. Right? Just to make sure you learn your chemical bonding. If you say that this is planar, then what is the hybridization state of this carbon?
No, this one.
Yeah. Is it sp3? Cannot be, right? If it's planar.
Yeah.
So it's not planar, in fact.
Oh.
Right? This one is testing you on the concept of chemical bonding, right? So what is the shape of this? If you were to just build a simple model to graph the shape of this, right? You will realize that this is the shape. This is not planar, right?
Yeah, it's not.
It's not planar. There's no way for you to make it planar, right?
Is this
So-
the 2O? Wait.
Yeah, this is the 2O lah. I should change it to O, right? So in fact, there's no plane of symmetry.
Oh my goodness.
It looks simple, right? That's why you have to fall into a trap before you learn why is that, right? So these are two oxygens, right? There's no way, there's no mirror plane or whatsoever, right? So this is chiral. Okay, so just don't fall into a trap. Next, I already finished chiral molecule. So chiral molecule, just use these two. Next, chiral center. If a center is chiral, then you will have a non-superimposable mirror image of that center. However, having a chiral center in a molecule doesn't necessarily mean that the molecule is chiral. For example, like this case, right? For this case, I have chiral centers, but is it overall chiral? No, because I have to rely on these two, right? So more often than not, most large molecules have many chiral centers and are chiral. So if the question is asking for the number of chiral centers, then only one condition needs to be met, which is there must not be a plane of symmetry cutting through that center, right? So the above implies that for a tetra-substituted atom, for example carbon, as long as the 4 groups attached are different, it will be chiral. So this is in fact an example of this. A lot of schools teach this as the concept, which is wrong, right? This is just an example. Later on you'll see why, right? So I believe you know how to do these kind of questions, right? You sure? What about this carbon? Right? Yeah, that's all. Yeah. Right? Very simple. So again, these are just generic examples, right? So you have your alkanes, you can draw the mirror image here, right? So next, you can also have sulfoxides, RSOR, right? What do I mean by this? If I ask you to draw RSOR, of course these two must be different. You have a double bond O, right? You realize that sulfur is from group 6, so there should be 6 electrons. 1, 2, 3, 4. There's a lone pair. Correct? So this lone pair can also act as a group, so that this is chiral. You see why, right?
So this one just count as one.
This is considered as 1 group, 2 group, 3 group, and 4 group. Just like your cis trans, you consider this as 1 group as well, right? So in fact, for this case, you can just draw the in order to not get confused, right? You can just draw it this way, right? And then draw the mirror image. Yeah. Same thing for next one, you've learned about complexes, right? So for complexes, they can also exhibit chirality. For example, you have this complex, you can draw the mirror image, right? Okay, how do you convince yourself this is different from this?
How? They cannot supersede each other.
Yeah, how do you convince that this is not the same as this? If let's say I give you a picture of an inverted Mona Lisa and a picture of an upright Mona Lisa, right? And then ask you, are these two paintings the same?
No.
What will you do?
Because they're inverted.
No, like you can just rotate it, right?
Yeah. So now I rotate.
So is it easier to compare things when they're upright or one inverted, one upright? Obviously when both are
one, wait. I mean when both are like
in the same orientation, right?
Easier.
So for this case, you will want to rotate one so that it looks somewhat like the other one, right? So for this case, how do you do the rotation? This is a very, very useful skill.
Oh.
Teach you once. L. Right, how do I rotate this the other way around? To make sure that this thing eventually ends up here, right? So first I'll number them 1, 2, 3, 4, 5, 6. So if I have this molecule, I turn it 180 degrees, right? 5 will still be on top, 6 will still be below, right? So L5 and L6. Right? So now if I rotate this whole molecule by 180 degrees, L3 will be here. L4 will be here. So this L1, this is L1, this is L2. L2 must be here. L1 must be here. So now I know that L5 is always connected to L2. L3 is always connected to L4. This is L4, right? Yes, sorry. This is L1. Yeah, correct, like that. Okay, and then L1 is always connected to L6, which is the one behind. And then I take this image, I compare with this one. They are definitely different. So this is how I convince myself in a systematic way, right? Nothing gets messy, right?
Yeah.
So next, nitrogen inversion, right? This is again something which only I teach. You might think that secondary, tertiary, and quaternary amines with different R groups can exhibit optical isomerism since it fulfills rules 1 and 2, right? Which is this. You might think that, hey, this one got 1, 2, 3, 4 different groups, right? This one got 1, 2, 3, 4, this one also got 4 different groups. But in fact, these two doesn't exhibit optical isomerism. The reason is because of a phenomenon known as nitrogen inversion, right? So what happens is that if let's say you have such things, these two, this R1, R2, R3 can actually flip upwards and this come down, right? This is just like going outside with an umbrella on a very, very windy, rainy day, right? Your umbrella just get inverted. So it's like the same phenomenon. So that's why these two isomers flip about very, very fast. So effectively, we don't consider this as chiral, right? But for quaternary amine, there's no way to flip, right? There's no way for your umbrella, that rod to flip to the other side, right? So that's why for this case, it can exhibit chirality, right? The next kind, same thing, only I teach, is what we call atrope isomerism, right? These kind are very, very interesting molecules. In fact, I would say this one is the most important one because that's when a lot of teachers will test, right? So atrope isomers are chiral molecules which do not have chiral center. So it's actually very, very weird. For all of these, they contain a chiral center, but for all of these, they do not contain a chiral center. For example, like this case, right? You have a biphenyl system. So this biphenyl system actually, if you look, you know that the phenyl ring is planar, right? They're actually orthogonal to each other. Why is it orthogonal? It's because if it's like that, right, there will be sterics between y and y, x and x. So it prefers to adopt this fashion. So once you have this fashion, you can actually have optical isomers as well. You can actually draw this out, right? The next one, which is the more important one, is allenes, right? For allenes, I already built a model of allenes, right? So you have this allene, and if I were to make his mirror image, it will be like that, right? These two are mirror images, and you can see that these two are basically non-superimposable. They're always different no matter how you flip it. So that's why it can exhibit optical isomerism. And some students think that, oh, this one double bond, why not cis trans? Wrong. Remember, cis trans must be planar. This is not planar. So there's no way for you to define a cis or a trans. Right? Like for example, if you look at the side like that, how do you define cis and trans? It's impossible, right? So therefore, these are optical isomers, right? They are not cis-trans isomers. The last case is this, right? This one I don't have to explain because it's exactly the same as this. Right? So it's another optical isomer. Right. Next part. Meso compounds, right? If a molecule has only one chiral center, then you will definitely be chiral. This is obvious. Similarly, if a molecule has no chiral centers, then you will definitely be achiral. It's also very easy, right? Sometimes, if a molecule has more than one chiral center, it can still be achiral. And for these kind of molecules, we call it meso compounds, right? So meso compounds are defined as compounds which contain chiral centers, but it is achiral due to the presence of a plane of symmetry or center of inversion. In fact, just now we already seen one, which is this, right? So these are meso compounds. So for now, can you just practice on this and tell me which are chiral compounds? It requires a bit of rotation. Right?
First and last. First and last.
No.
That means the in-between two already.
So how do you do such questions? Very simple, right? You have to imagine. You build the first one. So this is the first one. This is the first one, right? X is green one. So we can see that this lie on the same plane. So these will be pointing out towards you, these will be pointing out towards you. Is there a mirror plane?
Oh, this one is this one or this one? This one, right?
This one, yeah. Can see why is it this one?
Yeah.
It's just like that. Can see, So is there a mirror plane? We have to rotate it, right? There's no mirror plane. Right? So that means this is chiral. If this is chiral, this must be chiral as well. Correct. So it's these two. Right? Why is these two? Right? How do I get these two? I just swap these two, right? So the key takeaway for this you must know how to rotate. So for this is like that. Like that. Yeah, this one. Right? So this one there's a mirror plane. Exactly in the center. So this is a meso compound. This is a meso compound. Okay,
Well, in exam, you don't get to see that, and how you see.
You can remember what did I tell you just now? How to rotate, right?
Oh, you kind of counting the 1, 2, 3.
Yeah, correct. Okay. So for molecules, so as a summary, right? For molecules with no chiral centers, there's no is optically inactive. For molecules with only one chiral center, if there's a plane of symmetry, no, it won't be chiral, right? It won't be optically active. If there's no plane of symmetry, then yes, there's a chiral, right? For molecules with more than one chiral center, if there's a plane of symmetry, yes, no, you can read, right?
Yeah.
So in general, a molecule with n chiral centers and m geometric centers have 2 to the power of n plus m stereoisomers unless there is either a mirror plane or center of inversion. Just now already see, right? So let's just try this example.
These are two separate molecules.
Yeah, two separate molecules. Wrong. Right, I told you I won't ask easy questions, right? Remember what did I say here? 2 to the power of n plus m stereoisomers unless there is either a mirror plane or center of inversion. For this one, there's no center of inversion, but is there a mirror plane? Yes. About the center, correct? So how many? You can't just use this method. So for this, I present to you another method, right? So there are 3 double bonds. So each double bond can either be cis or trans. So trans is one possibility, right? Of course, you have cis. Next, you have trans cis. You have cis trans. Do you consider trans cis? No, because remember there's a mirror plane in the center, so these two are exactly the same, right? Correct, huh? So next, I consider cis trans. Trans cis, these two are same once again. And I have cis trans cis. And these are all the possibilities I have. So in total I have 1, 2, 3, 4, 5, 6.
So for this time must do manually?
Yes. But trust me, they won't ask a lot, right? You can go Google, there's a general formula, right? But the formula depends on whether you have odd number of or even numbers, right? But I think the most they can ask is 3, right? Otherwise it gets too tedious. This one you can go back and practice yourself, right? Same thing, use the... But you have to know that for this case, right, there's a mirror plane, of course. This is not chiral because these two groups are the same. Same. So the only chiral, the only groups responsible is this double bond and this. Right? So this one have 3, this one have 4. So this one have slightly more. Right? So for the rest, this part you can go read yourself. Again, this part you can go read yourself, right? Usually I teach some extension kind of questions. For example, like they are not planar, etc. Right? Okay. I go through the 3 course first. A molecule with the formula of this can contain 2 double bonds. This one you can calculate, right? I already told you the formula, so you just I forgot what's the answer, right? I usually don't make answers. So this one you can go back and calculate. Right? Chain isomers have the same physical properties.
No.
You sure? Chain isomers, they still have... Yeah, correct. Okay. Positional isomers have the same chemical properties, which is correct. It's just the group, right? Geometry isomers can be separated. This is true. Optical isomers cannot be separated. This is true as well. You can write the correct answer, right? Next one, the cis isomer has more effective backing, which is false, right? If there is no double bond within a molecule, then there will not be any geometry isomers, which is false, right? You can have cyclic molecules, etc. Next, cyclic alkenes do not have cis isomers. Blah blah blah. Yeah, correct. Yeah. Okay. A molecule with 1 chiral center must be optically active. This must be true, right? A molecule with 2 chiral centers can still be optically inactive. This is true, which is your meso. A molecule without any chiral centers will not be optically active. This is false. Okay? Because I don't have chiral molecules. This one is your atrope isomers. Next, optical isomers have similar chemical and physical properties but different biological properties. This is correct. Okay? The exact proportion of each enantiomer can be made known if the specific rotation of plane polarized light for the mixture is known. This is true, right? So if you have 50-50, you won't rotate plane polarized light. So the molecules below will rotate plane polarized light. This one have a center of inversion. This one have a plane of inversion, right? So these are plane, so they will not rotate plane polarized light. So this is false. Chirality is unique, which is false, right? You can have sulfur, you can have other molecules. A compound with n chiral centers and m geometry centers must have a total of this, which is false, because just now we have seen, right? It can be a meso. The 2 molecules below are enantiomers. For this one, you just have to rotate a bit, and you'll see that your answer is correct. Okay. Cyclopropane, cyclobutane, and cyclopentane are planar molecules. This is wrong. They are not planar, right? Why they are not planar? Cyclopropane, this is sp3, sp3, sp3. Usually when we draw like that, it looks like planar, but take note there's hydrogen sticking out and sticking in, right? So it's not planar. Same as this and this. Okay, so the rest you can go and the questions as well.